Boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists, and that's with Helen Scales. Hello, Helen.
Hello.
And hi, Dave Ansell.
Hi there.
And I'm, of course, Chris Smith. Now, this week, scientists have discovered the ultimate in adoption, a caterpillar that gets brought up by ants. But why do they choose to help a butterfly? Well, we'll be finding out shortly. Also, why sea level rise due to global warming might be much worse than we first thought. And that's because scientists had previously overlooked the possible impacts of gravity in the equation. And also, we'll be hearing about a new way to diagnose arterial disease. But get this, using urine. And we'll be finding out how very shortly. Helen.
Thanks, Chris. This week it's also our science question and answer show. So we'll be tackling all your science questions, including finding out why the sound of fingernails is so awful when they're dragged down a blackboard and it sends shivers down your spine, why chewing a piece of metal foil makes your fillings taste all funny, and why is it that the sea is salty? Dave.
Thanks, Helen. And in a special Icy Kitchen Science, we're going to have a bit of a race. All you need is a microwave, some ice cubes, and a bit of water. And it's very easy to try at home, so if you want to have a go, grab those along, and I'll explain what to do shortly.
Thank you, Dave. That sounds intriguing. I presume you're going to be using the defrost function. Anyway, if you would like to get in touch with the programme and ask us any science questions or give us some feedback, then do get in touch. The email address, chris@thenakedscientist.com.
The Naked Scientist Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This week, scientists have discovered the most incredible piece of evolution, which is also nature's most outstanding example of adoption, I'd like to think. This is Jeremy Thomas and his colleagues. They're at Oxford University, and they've been studying a particularly rare species of blue butterfly. It's called Maculinea rebeli. And this species of butterfly gets its caterpillars inside the nests of ants. And once they're inside the ant's nest, the ants look after the caterpillar. In fact, it does 98% of its growth inside the ant's nest, and somehow it persuades the ants to look after it, to nurture it, and when times are tough, even to feed their own brood, their own ant grubs, to that caterpillar so that it survives. And the big mystery was, well, how does it persuade ants that would normally eat caterpillars to treat it like a friend, not a foe? And initially, scientists realised that the caterpillars were beginning to smell like ants. What they do is to secrete various chemicals through the skin of the caterpillar, which mimics the smells made by ants, so ants realise that they're probably friend and not foe. But that couldn't be the whole story, because these caterpillars were being treated almost like royalty inside the ants' nests. So what the researchers did was to thread a very tiny series of microphones into real ants' nests that had these caterpillars in them, and to listen to the sounds that the ants make, and also listen to the sounds that the caterpillars make. And what they discovered is that the ants talk to each other with little clicking noises that they make by grating together two rough surfaces on their abdomens. And the sounds that the queen ants makes are slightly and subtly different than the worker ants, which is how ants tell queen from worker ant. But then they recorded from the caterpillars as well and showed that these caterpillars have evolved to make the same sounds as the ants make. And so what they're able to do is to fool the ants into thinking that they're dealing with a queen, and so they treat it like a queen. And this is an amazing example of convergent evolution, where because these ants and these butterflies live in the same sorts of areas on Earth, they've slowly evolved and adapted to utilise one another. And this particular species has gone one step further. And we're very lucky because Jeremy Thomas sent me some of the recordings of the sounds that they got during the experiment. So here is the sound of the ant queen. So that's it scraping the back end of the abdomen against itself. So that's the queen. Let me just play you the caterpillar by comparison. So what you'll notice is it does sound subtly different, but if you digitally analyse those sound traces, what you find is that they are extremely significantly similar in terms of statistics and the frequency distributions and the types of sounds and the order they're coming in. And this is enough to fool the ants into thinking that they're dealing with another ant, not a caterpillar.
Have they tried playing these sounds back? And do the ants do the same thing to a microphone that's making the same noise?
Absolutely.
They
in fact, that's how they prove that's what's going on, because they made the recordings from microphones threaded inside the nest. And then when they played this back through a little speaker near some ants, they looked at what impact it had on the ants. And when they played sounds from the caterpillar, they behaved in an identical way as when they played sounds recorded from a queen ant, which is that they have this on-guard behaviour. They flock to the speaker, they stand up on their hind legs, they open their jaws, and they put their antennae to attention. And if anything comes near, they attack it. So it's almost like the caterpillar's got even better at recruiting this kind of behaviour than the actual queen ant itself.
It's extraordinary. Isn't nature just fantastic? And I'm going to stick with nature for my first story. And if you've seen the movie Finding Nemo, you'll know that Nemo the clownfish got lost and he had to try and find his way back home, back to his home reef. And now it seems that the Disney animators might have been onto something, because a study published in the journal PNAS, led by Philip Munday from James Cook University in Queensland, Australia, found that clownfish may indeed get lost if the oceans become more acidic. And that's likely to happen as more carbon dioxide enters the atmosphere and dissolves in the sea, forming carbonic acid. Now, we already know that many coral reef fish spend the first few weeks of life as teeny tiny larvae drifting in the open ocean. And we also know that they then follow their noses and their ears, sniffing out and listening to the sounds that lead them back to the reefs where they were born, which is, I think, another incredible part of nature. Absolutely wonderful. But the problem is, it now seems that as the acidity of seawater increases, fish might actually lose their sense of smell and have trouble finding their way home. Now, Munday and his team looked at newly hatched clownfish larvae. They put them in the laboratory and gave them a choice of swimming in water in a tank that was containing two different chemicals. And in seawater of normal acidity, the clownfish preferred to swim in a plume of water that smelt of rainforest trees, which you might say, why on earth would they do that? But in the wild, they actually tend to live on reefs that surround vegetated islands. So by following the smell of the rainforest trees, that would take them back to their homes. What happened was, when they increased the acidity in these laboratory conditions, the clownfish instead chose to swim in a plume of water that smelled of swamps. A nasty smell, actually, that we would all avoid, but certainly clownfish normally avoid these types of smells and don't swim towards areas of swamps. Now, it might not sound like a huge difference, swamps or rainforests, but if wild fish really start to lose their ability to find the right sort of habitat, it could really spell disaster for entire populations and ecosystems. So I'm afraid this study really spells out another gloomy forecast for the changes we might see as carbon dioxide continues to build up in the atmosphere.
I guess the one advantage that fish have is they produce billions and millions of young, or thousands of young, and therefore if a few of them can find their way home, those are the ones which are going to be able to breed, and so you might quite quickly evolve fish which can manage it, if only a very small proportion can find their way home.
You're right, actually. I mean, they do have that ability to produce lots of offspring, and they expect a lot of them to die, because if they didn't, then the oceans would be completely full of fish. So there is that possibility. So let's hope there is some hope that the fish will be able to cope.
One quick question, Helen. The levels of acidity change that they inflicted on these fish, are they thought to be realistic in terms of what we think the environment will turn into subsequently if we carry on business as usual releasing CO2? I
believe so. I mean, we already know that in the last 200 years, the acidity of the oceans has already increased significantly. I think decreased, sorry, by about 0.1 of a pH
Acidity
unit.
Gone up, pH gone down.
That's right. Mustn't get those two mixed up. Sorry, Chris. So the pH has gone down and the acidity has increased already. And so therefore there are models that predict that I think they were looking at, in this scenario, how it looks like it will be in the year 2100. So we already know it's changing, and it probably will continue changing. Obviously, we might not know exactly how, but certainly those changes are happening.
Certainly worrying, though, isn't it? Dave?
I've got another story on global warming. Now, if the world's going to warm up, then it's quite obvious the sea's going to rise. As the water warms up, it expands, so it takes up more space, so the seas are going to get higher. And as ice on continents melts, it's going to dump more water into the ocean, again making them higher. Now, many models predict the melting of the West Antarctic ice sheet, which is a big ice sheet on the sort of pointy bit of Antarctica which sticks up north. And this is predicted to produce about a 5-metre rise in sea levels. But researchers from the University of Toronto have noticed these models haven't taken something quite important into account. This is gravity. Everything with mass attracts everything else with mass. So they're all pulling each other. That's how planets orbit stars, etc., etc. So the 22 billion tons of ice in this ice sheet are going to be attracting the seawater around them. So this sort of forms a bulge and pulls the seawater around it. So when the ice sheet melts, you not only get all that water pouring out everywhere, but that bulge, there's less ice pulling all the seawater towards it. So the bulge is going to drop as well.
So what sort of difference will that translate into? Is this a trivial effect, or is that a lot of water that's being locked away by gravity as well as ice?
Well, I think overall over the whole Earth, that's probably going to, on average, produce that half a metre effect. But it's also going to have another effect, which is you're moving a whole lot of mass, which is off-centre on one side of the Earth. And the Earth is a gyroscope. And when you do that, you can actually move the axis of rotation of the Earth.
So you'll adjust how the Earth is spinning?
Yeah.
What will that do to the distribution of land and water on Earth?
This means that the water's going to get more deeper in some places. So places like North America, it's going to get extra deep. So it's going to rise another 1.5 metres on top of the 5 metres, so 6.5 metres. Whereas places like around Antarctica, where this boulder is dropping away and it's actually almost going to fall. It's only going to rise a little bit, far less than you'd have expected.
It's amazing to think that we didn't think of that, though, isn't it? Because people have even used the same phenomenon to explain Mars, because on Mars you can see these ancient tide marks going back 4 billion years or so, and they show huge tides on Mars, but they're also in the wrong place to a certain extent. And scientists realise that the huge mass of Olympus Mons, the biggest volcano in the solar system, which is on Mars, had caused the planet to change its axis of rotation very slightly, and thus pulling the crust all in one direction and making these tides appear much higher than they originally were. This is the sort of same phenomenon, but because it's close to home, I guess we totally overlooked it. And
the other thing is, it's probably a much smaller effect than Olympus Mons, but because the oceans are 5,000 metres deep, you only need a sort of 1 part in 1,000, 1 part in 10,000 effect to have a notable effect for us living right on the coast.
What about this part of the world and East Anglia? We're already just about above sea level. The Netherlands, the same story. Will they be impacted?
Around here, they reckoned it was probably maybe only about 1/10 of a metre on top of... the 5 metres is a big problem. It might be a little bit more, but we're probably, from this effect, not doing too badly.
It's all a bit worrying. Well, I'm going to take my news this now onto the medical world, and news that researchers have reported a new way of diagnosing whether someone is likely to develop coronary artery disease, or CAD, by testing the chemicals present in their urine. Well, CAD is a major cause of death around the world, and currently the only way to diagnose it is to conduct an angiogram, and that's expensive and it's invasive. It involves really injecting dye into the blood to show up on x-rays how badly the blood vessels around the heart are getting lined by fatty deposits or plaque, and that they can build up and restrict and eventually block the flow of blood to the heart, causing a heart attack. Well, now a team of researchers led by Karl-Heinz Peter from the Baker Heart Research Institute in Melbourne, Australia, have identified 17 specific peptides, and they're the molecules that make up proteins, in the urine of people who are diagnosed as having CAD using angiograms. Well, their study is published in the Journal of Proteome Research, and it describes also how they actually carried out a blind test of these peptides. They first screened the urine of a group of volunteers and then subsequently gave them angiograms to see if they were right about the prediction of whether they had CAD, and they found that they were right about 84% of the time. The urine actually backed up the test that they found, the diagnosis based on the angiograms.
Do they know why these things change in the urine when you have blocked arteries? What's going on?
Yeah, well, they actually found this direct link, which is very neat, between the peptides and CAD, because the researchers also looked at the same, they found the same chemicals in the fatty plaques that line the blood vessels of people who have the condition. So that's presumably why the peptides are finding their way via the blood into the stream of urine, and that's what you can test for. So it's pretty early days now to see this test being rolled out, but I think it really points the way towards perhaps a cheap and non-invasive test that could help pick it up much earlier, because the key is that if you know you've got this condition early, you can do things, change your diet, your lifestyle, really to help try and control the development of the disease.
Certainly an important area to look at. Thank you, Helen. Now, also in the news this week, researchers have found evidence of the earliest animal life on Earth, and it shows that complex life was actually flourishing here much earlier in Earth's history than we first thought. And Dr. Gordon Love, who's at the University of California at Riverside, has uncovered the chemical fingerprints of sponges, which are thought to be one of the first forms of animal life, and he found it in rocks that are up to 750-odd million years old. Hello, Gordon.
Yeah, hi there.
Welcome to The Naked Scientist. So tell us, what have you actually done?
So what we did was we looked through rocks in South Oman, and we have an unusually continuous sequence of rocks and an opportunity for looking at the geobiology of this time, and we found a continuous 100 million year record of sponges going from a time known as the Cryogenian, which has been associated with two major glacial episodes and extending right up into the early Cambrian period.
So where did you get these rocks from? How did you come by them?
This came out as part of we're fortunate we were working with an oil company in Oman, Petroleum Development Oman, and this is currently the only area in the world where people are actually commercially producing vast amounts of oil from rocks of this age. But through our contacts with the oil company, then we had access to very pristine material from drill core. So that became very, very important in having this stretch of time, and also to the fact that these were very thermally well preserved rocks that we were dealing with.
If you look at the fossil record, though, and this frustrated Charles Darwin, that life appears to pop into existence about 540-odd million years ago, because prior to then, presumably, there weren't enough animals with hard body parts that could be fossilised. You've presumably run into the same problem, so how do you know that you've got sponges going back 750 million years?
So these are one of a number of steroid structures that we detected, and the precursors of these molecules of the sterols are very specific to a class of sponge called demosponges. And actually sponges make a wide range of really unusual natural products which really interest the medical field as well. But in this case, despite about 4 decades of research, then these have never cropped up. These sterol precursors have never cropped up in single-celled organisms.
I see. So what you're saying is that you're able to unlock from the rocks chemical fingerprints, if you like, molecules made by those early sponges 750 million years ago, that when the animals died and were locked away in those rocks, although the animals, the vestiges of them physically are gone, their chemical legacy lives on, and that's what you can detect.
Yeah, I think that's right, and this is an important factor with Darwin. The puzzle about the lack of information is that I think if you look at smaller and smaller scale, then there's a tangible record for animals significantly predating the Cambrian explosion.
And just tell us a little bit about the technique to get these molecules out of the rock. So you get your rock sequence from the oil driller. How do you then get out of the rocks the chemicals from the sponges, and how do you know which rocks they've come from and that they are actually made by the early sponges all that time ago?
Okay, so we did a couple of approaches. So the conventional way in organic geochemistry is to powder the rock after you've cleaned and removed the outer parts, do some sort of solvent extraction technique, concentrate up the steroid components in a fraction and analyze these by gas chromatography mass spectrometry. So we found really abundant amounts of these steroids in all the different rock formations that we looked at. But to confirm that we were actually, it wasn't just coming from migrated oil, perhaps which resides in the younger part of the section, then what we did was we isolated what is an organic polymer. So the bulk of sedimentary organic matter is actually insoluble, and it can't migrate anywhere, and it makes up a large macromolecule. And we basically broke chemical bonds by using a technique where we heat up samples with high hydrogen gas pressure. And so when we looked again at the steroid composition, we saw that yet again these sponge steroids were abundant in our products, and in that way we could more confidently equate the age of the markers with the age of the rocks, which we got from uranium-lead isotope dating.
So this shows you that those rocks of that age had complex animals like sponges living in them. Why do you think that they're there? And what does this tell us about the origin of complex animal life on Earth around that time?
Yeah, I think so. Most of the rocks, the depositional environment that we were looking at when we looked at these rocks on Oman is shallow marine waters, and I think originally the simplest animals like sponges would have colonized the seafloor on the shallow continental shelf, and it could have been tens of millions of years later before they could pervade into deeper water environments. But I think it's telling us that at this time, in terms of the environment, there was finite levels of dissolved oxygen near the seafloor, at least on the shallowest water environments.
And does it fit with what we understand was happening elsewhere on Earth at the time? Because usually when you see an explosion of some evolutionary process, there's something going on in the climate or in the Earth's other processes. So can you marry this observation with anything else going on at the same time that might explain what you're seeing? Yeah,
the huge thing that's going on at the time is now we've pushed this back, the first appearance, into the time frame of the two vast Neoproterozoic glaciation events. And my feeling on this is, so I've looked at many rocks of age which are older than the first glacial event, and I have never seen any convincing evidence for sponge biomarkers. And I think that these major glacial events radically altered ocean chemistry in the aftermath by shutting down a lot of ocean-atmosphere interaction. And it seems, although we're trying to still get a handle on how exactly the chemical composition changed, it seemed that they opened up avenues for new niches, especially for organisms which could filter feed on the seafloor.
So it's amazing to think that you could get complex life out of an ice age. Thank you very much. That was Gordon Love, who is from the University of California, Riverside, and he's got a paper in this week's edition of the journal Nature explaining how he has found evidence for the signature of life in rocks going back up to 750 million years old.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith, me, Helen Scales, and Dave Ansell.
Now, there is, of course, also another way you can listen to The Naked Scientists, and that's in Second Life. If you want to listen there, you just go to Second Life and you find the Scilands continent and you look for the Naked Scientists mansion, and you should see our collection of friends and listeners all assembled there. So hello to all of you, we're watching you, and you can join in with them and discuss the show and ask and have your questions answered.
We've had an email from Abner in Lipa City in the Philippines, and thank you very much for your email. And it says how our shows have been helping through the journeys on their way to her daughter's music lessons in Manila, through the heavy traffic, that it keeps them going, and that they actually managed to understand our British accents, which are different to the American accents, and that they like that very much. Well, thank you again for your email. We're very glad that you're enjoying the shows.
Thank you, Helen. Now, it is The Naked Scientists, Chris, Dave and Helen, and as usual we do an experiment that you can try at home, and Dave has cooked up an exciting bit of kitchen science for you this week, although this is a chilly one, which is ideal because it's been a bit of a chilly week. Dave?
Yeah, it's been very cold outside here in Cambridge. We've got quite a simple experiment. What we're going to do in a minute, I'm going to have to go up into the kitchen in the BBC here.
It'll be a bad experience.
I wouldn't like to comment. What we're going to do is try and see which is going to melt, whether ice is going to melt in a microwave or water's going to boil, which is going to happen first. And have a bit of a race. So what I'm going to do is get some ice cubes, 2 or 3 ice cubes, put them in one glass, weigh how much ice is in there, then put the same amount of water in another glass, then put them both in the microwave, the same distance away from the centre, because a microwave has hot spots in it, and then the turntable turns the food through those hot spots. So you want the 2 glasses to have the same heating effect, to make it a fair race. So we're going to put them the same distance away from the centre, then put the microwave on for a bit and see whether the water boils first or the ice melts first.
And presumably people can try this at home as well?
Yes, just be a bit careful, because obviously putting stuff in a microwave, it's going to be very hot, so don't go grabbing in it and shaking it around. The other thing you might want to watch is it is possible, if you're heating water in a microwave, that you can actually cause bits of it to go over 100 degrees centigrade, and then if you shake it, it can all of a sudden boil all over your hands, so don't touch it for a couple of minutes after you've had it in there. Let it cool down.
Thank you, Dave. So we look forward to that. What do you think is going to win the race if you microwave either water or ice? Is the ice going to melt first, or is the water going to boil first? Basically, it's the same sort of increase in temperature, so there shouldn't be a huge difference between the two, or one ought to work at the same sort of rate of the stuff. They're both made of water, but we'll find out. If you want to have a go, grab a couple of glasses, ice cubes in one, water in the other, microwave them for the same amount of time. Helen, got a question here from Merin, who says, why do Portuguese men of war, those are blue bottle jellyfish, beach themselves?
It's a great question. That's fantastic. Well, Portuguese man of war, a type of jellyfish, but actually they're not. They're lots of different individual animals that live together. They're not really considered as being a single organism, which is rather intriguing. But they can't actually swim. They don't have a way like other jellyfish of pulsing their tentacles and moving. So they're basically at the mercy of winds and currents and what's going on around them. So they have this lovely blue and sort of tinged in pink pneumatophora, sort of float full of gas that floats them on the surface, and that catches the wind, and if the wind is blowing in that direction, it can beach them. And the really cunning thing about these guys is that, like humans, Portuguese man of war can be left-handed or right-handed. About half of the population has this pneumatophore that's shaped towards the left and half that's shaped towards the right, which means that they will go in different directions if the wind blows in a certain direction. I think that's just very cool indeed. You can imagine why that might be a good thing, because if it means that half the population will respond to will get swept up on a beach if the wind's going in a certain direction, and some of them won't. So they won't all necessarily land up on a beach, because that's not great. They usually get trodden on and they will desiccate pretty quickly and dry out if they do end up on a beach. But it's all very much at the mercy of the the elements. They're stingy
beautiful,
beasts.
though, aren't they?
They are beautiful.
I saw them when I was in Australia. Some of them were doing exactly as you say, being blown up on the beach because they have this sail on the top which pushes them along.
And you got stung
very long
by one,
tentacles.
didn't you?
In America, I did, and not in Australia because I knew what they were by then, so I avoided them. But they're very beautiful, as you say.
They're wonderful. In fact, I have to say, I've got a little story about the first time I saw a Portuguese man of war. Was also the first time I saw my own very personal seahorse. You know, I'm a bit loopy about seahorses, and I had seen a couple when I was diving, but someone else had pointed them out to me. I was in Belize last year, and a Portuguese man of war had been blown into the dock next to a jetty, and I was wandering along, and I noticed it and stopped and thought, well, that's cool. Got my camera out, started taking some pictures of this Portuguese man of war and its tentacles everywhere. And I'd gone to that pier to look for seahorses because I'd been told there might be some there. So I'd stopped and I finished with the Portuguese man of war. Then I thought, I suppose I should have a look for this seahorse. And I didn't move. I stood in the same place, looked across, and there was my little seahorse clinging to this side of the jetty. And I spent the next half an hour trying to swim around with it and not get stung by the Portuguese man of war, which you'll be happy to hear I didn't.
It's interesting because some creatures can survive and not get stung by them. There are some fish that actually live amongst those tentacles, and some that can even take the nematocysts, the stinging cells, and incorporate them into their own body and use the poison, can't they?
There are definitely some odd things going on. And you remember I was talking just now about the clownfish, and they live in anemones, which are a relative of all the corals and jellyfish and things, and also are stinging. And I know that those guys, when they're young and when they're born, rub themselves up around the base of the anemone and actually cover themselves in a type of slime that then makes them immune, and they don't get stung by the tentacles. That's why they can snuggle in and live in the tentacles of the anemones, and that's what the clownfish are doing. So there's all ways around it. It's
a bit like the caterpillars in the ant nest making themselves sound or smell the same. Maybe the fish are doing a similar sort of stunt. Thank you, Helen. This is The Naked Scientists with Chris Smith, Dave Ansell and Helen Scales. It's The Naked Scientists Science Phone-In, so if you have a science question for us, our email address is chris@thenakedscientist.com. In a second, we'll be talking to Dave Jones, who wants to know why, when it snows, appropriately this week, the railway lines on trains that have the power running through one of the rails don't short out.
Keeping you abreast of the world's best science. The Naked Scientists.
Dave, you're live on The Naked Scientists.
Hi there.
Hi, tell us about this question.
I was wondering why it is when you get piles of snow building up on the railway lines that you don't get a short circuit between the conductor rail and the ground beneath it, or the track rail that runs alongside. After all, if we were to stand astride these two rails barefooted, they would make it effective. That would make an effective short circuit, even though our bodies are composed of as much as 2/3 water. So that's my question, really.
Yeah, there's a couple of things. The first one is that pure water is quite a good insulator. In fact, my girlfriend's dad used to work in a lab with huge amounts of very high voltages and very pure water. So if water's pure, it doesn't conduct electricity very well. You need some salts in it.
Why doesn't it?
Basically, if you can conduct electricity in a liquid, you really want some free ions. So you need some positively charged things and negatively charged things. If you've got some salt in there, the salt splits up into negative chloride ions and positive sodium ions, and the positive ones will move to the negative end of the battery, and vice versa, and so you get a current flowing. So that's one thing. I think basically they do lose quite a lot of power through things shorting them out, but probably don't get you get some gentle losses through there all the time. If there's anywhere where you do get a lot of power dumped, so if you get a particularly conductive bit of snow or ice, it's going to get a lot of power going through it. It's going to get very hot. It's going to melt and move away from the rail, and so it immediately breaks that short circuit.
Is it worth bearing in mind that the voltage on things like the London Underground is a lot lower than when you've got trains doing very long journeys on very long distances where it's much more economically sensible to use high voltage?
Yeah, the rails on the ground, the rails are about 600 volts. The overhead lines are about 25,000 volts. Because of this effect, if you had a 25,000 volts on a rail, you'd get sparks jumping to the ground, and you get large currents going through everything, and you also kill a lot of people. So so it's not actually lethal unless you actually touch it. So yeah, I think they probably do lose quite a lot of power through them, but less you'd expect, because anywhere whether you do get a short, it's going to burn out.
On a foggy day, if you go near to a pylon, very high tension cable, say 500,000 volt pylon, 400,000 volts we use, don't we? You can hear them buzzing, and as the mist is settling on the insulators supporting the cables, and you're getting exactly the effect you described, that little bit of kind of arcing and presumably it then vaporises the dampness there, and that goes away, but then some more settles.
Yeah, but whenever it vaporises, it's going to expand the air and cause a bit of a
Great question.
sound.
Thank you very much, Dave.
We had a question here from Lars Einar Jensen. He wants to know, why does the sound of nails on a blackboard elicit a physical response?
Oh, it's making me cringe now just to think about it, actually. This is quite a commonly asked question, and the answer is psychologists and scientists don't know for sure, but one very plausible theory is that when you run fingers down a blackboard, the frequencies that you hear are very high-pitched. And the high-pitched frequencies are very similar to the frequencies that animals produce when they're in distress. And so one argument is that we are genetically programmed and tuned in to be sensitive to those frequencies, because that may alert us that an animal, one of our own species perhaps even, is in distress. Perhaps it's being attacked or eaten or is in danger. And therefore, by galvanising your attention and making you wake up and pay attention to that noise, you're therefore on high alert, and you can make plans to run away or fight or whatever like that. So I think that's probably the best explanation there is for that at the moment.
I like the idea of an experiment on other animals to see which ones are sensitive to nails on blackboards. We could put them in rooms perhaps and see which ones jump the most when we scratch our nails down.
Dave, got a question here from Susan Langley, who says, how do scientists find the weight of the moon?
It's an interesting question. Okay, the way they do it now is basically that if you've got something that's orbiting the moon, basically its weight is going to produce gravity, so the stronger the gravity, the faster it's going to have to orbit. So as soon as you put a satellite orbiting the moon, you can measure its mass quite accurately. In fact, by looking at how a satellite's orbit changes as it goes around the moon, you can actually see little tiny variations of mass caused by mountains and things. They get very, very accurate maps of the gravitational map of the Earth, and you can actually find things like ore bodies, because if you've got some very dense rock somewhere, then that's going to be slightly more gravity and the satellite's going to move down a bit. In the distant past, you could probably work it out by the size of the tides on the Earth, because you know how far away the moon is, you know how strong the gravity is on the Earth, and then by working out how much of an effect the moon has on the water, you'll be able to get some idea of how much mass there must be in the moon.
We also know that the tides on Earth used to be much bigger than they are today, because the moon and the Earth were much closer together, and there are fossilised tide marks that geologists have uncovered which are metres in height. And because the moon has slowly migrated away from the Earth, because it is moving away from us by about 3 centimetres a year, you end up with progressively smaller and smaller tides. So we're now down to the more reassuring sort of several metres rather than the hundreds of metres that they were getting at one time.
And that effect is because the Earth's the tides are slowing down the Earth and also speeding up the moon, and you can actually detect the slowing down of the Earth, because 200 million years ago you can look at how many days were in a year, because little corals grow a little line every day in a year, and then you can see it ranges in a year, and you can see there were over 400 days in a year about 200 million years ago.
Thank you, Dave. A quick question for you, Helen. This is from Nart, who says, how do tube worms move between different hydrothermal vents?
That's a great question. These are these wonderful 2-metre-long creatures, the giant tube worms anyway, that live in the middle of the ocean, very, very deep down in the deep, dark oceans where there's no connection to the light, and they only actually survive because they have these symbiotic bacteria that harness chemicals that live inside them. How do they move from one vent to another? Because they do live in very clustered environments a long way apart from each other. And there have been a couple of different studies that have looked at the genetics, and because, well, firstly, actually what they did was found out how long their larvae can live for, because the one theory is that they have eggs and sperm, which we've seen fertilising externally outside the worms. They let go of the eggs and sperm, form a larvae, and in the laboratory, those have lived for about 38 days. So the idea is that that's enough time for them to hitch a ride on a plume of water, and we know that there are these neutrally buoyant plumes of a mixture of hot and cold water, very, very deep down. We're talking kilometres down in the middle of the Pacific Ocean here, and that's enough time for them to drift and find another vent for them to live on. And these are also very short-lived things. These hydrothermal vents come and go as changes in the sea floor take place. So really they're quite ephemeral, and that's one thing they've done. And genetics have shown that that's likely to be what happens, that you've got very distinct populations that are sort of fed by just a few larvae arriving and starting a new population as new vents open up and new black smokers and things like that. We're talking 400 degrees centigrade. Crazy, crazy ecosystems.
It's amazing, isn't it, to think what's down there. This is The Naked Scientist. So Chris, Dave and Helen, we're answering your science questions for you. If you'd like to ask us anything, the email address is chris@thenakedscientist.com. We've had a bit of clarification on train voltages from John in Warrington. He says the third rail on things like Thameslink is 750 volts, and the overheads, as you say, Dave, 25,000 volts, and Thameslink is dual voltage, so presumably you can have hybrids running there. But we are also doing an experiment this evening, and Leon in Lowestoft has had a go, and he said his water boiled first. But remind people who may have just joined us what you're asking people to do, Dave.
Basically, try get a few ice cubes, try and put the same weight of water, so then one glass, same weight of water in another glass, put them in a microwave in equivalent positions, and see whether the water boils first or the ice melts first.
Now today, as well as answering your science questions, we're also going to take a look at what's happening in the world of technology. Here's Mira Senthilingam.
It's time to find out what the world of technology has to offer in 2009. So this month, I'm in the Business Centre for BBC News Online, and I'm here with our resident tech expert, Chris Valence. Hello, Chris.
Hi, yes. There's a reason why we've come up here, and that's so I can pick the brains of the BBC's resident tech expert, Mark Ward, who is the technology correspondent for the news website. And we're going to chat about trends in technology, because it's the start of the year, and there's one event which really showcases that for the tech industry. CES, the Consumer Electronics Show, and Mark, you were there. It was at the beginning of January that the big conference, the big jamboree happened. What was being showcased?
Well, lots of things, really. I mean, it's a consumer electronics show, so that, the clue's in the title. I mean, there's just everything was there. The big surprise, though, was I was expecting lots of really funky, shiny stuff. But actually, the big thing that was there was TV. Bigger screens, obviously, but more stuff to do with your big flat panel TV that you bought probably last year. Be that adding web bits to it or, doing more with your high-definition movies and things like that. TV was the star of the show, no doubt about it.
And it was a bit 1950s as well, 3D TV.
But yeah, this was very much the kind of next generation of it, though. It's stereoscopic, so glasses you still have to wear, but not and certainly a better quality of 3D. But the problem is that for all the talk, it still means you're going to have to buy a 3D capable set. That's going to be pricey, and there's very little content out there at the moment. Broadcasters are saying they will when there's content, and the content makers doubtless will say we'll make it when there's an audience. So at the moment, it's a lot of plans, a lot of sound and fury, but precious little action.
But we have seen things like IMAX, which have, I suppose, a similar problem. You need a huge cinema, you need special cameras. They have kind of taken off, so it's not hopeless for 3D TV.
No, there's a lot of commitment in the kind of film industry to do it, and I think sort of, in 5-10 years' time, maybe, we're going to start seeing that percolate through. But people keep their TVs for a long time, and if you just bought one, you're not going to spend the same amount of money again just to get at, 100 movies or something like that? Well, there's a vast catalogue of better stuff you could get at.
Well, I think for 2008, I've got in my hands one of these little tiny netbooks, these small, very, ultra-portable laptops. They're not very expensive, and they've been a real hit. Is that going to continue next year, at least according to the people at CES?
Yeah, definitely. There's a lot of tiny, shiny computers on show. There's a lot of netbooks now, about 15% of the PC market. Grew by 100% or so last year. Probably going to do the same this year. But I think at CES what we saw was the end of the compromises that you have to make when you buy one. Typically it means they're a bit slow, graphics aren't great, battery life can be a bit problematic. Whereas at the show we saw much longer battery lives, much more powerful processors, and graphics are starting to improve as well. So you might be able to play decent games on it and certainly show some video.
But times are hard. Was that affecting what was on display at CES?
Well, definitely. There's certainly some stats quoted about sales figures and things like that. And certainly in certain sectors, you're starting to see a shift from the kind of maximum that people can afford in terms of, say, a flat panel TV to something they're happy to spend. So you see a bulge around the sort of 32 to 40-inch kind of sets rather than sort of bigger than that. And certainly a lot of people, they were saying that actually the consumer entertainment might hold up pretty well, actually, because people tend to have got their flat panel TV, they've got their games console, got their smartphone, and now they want to do something with it. So games, movies, those kind of web-based services are probably going to be pretty popular the next couple of years as people stay at home rather than go out and save that money.
Well, Mark, other than what you saw at CES this year, is there anything else you're looking forward to in particular?
Well, I think there's a growing emphasis on green computers, green computing, green electronics, that kind of thing, because I think Groucho Marx said about Doris Day he knew her before she was a virgin, and I suspect that's the same with a lot of electronics companies, that they've discovered they're not as bad in the green statistics as they thought, so they're touting that as something of that people should pay attention to. But I think people are pretty sceptical, but I think it's starting to figure in people's perceptions. So, beyond brand, beyond price, people are going to start taking those green credentials quite seriously.
And how about you, Chris? What have you seen that's coming up this year?
Well, I'm interested. It's not necessarily brand new for this year, but I think we're going to see more of it. And people employing this technology creatively. I'm interested in these SLR, these single-lens reflex cameras that can shoot video. There are 2 on the market at the moment, very different price ranges. But the films that they produce are really interesting because you can change lenses, which you can't do with a cheap consumer camera. You can put on, wide-angle lenses, zoom lenses. You can even do those tilt-shift lenses, make everybody look like little tiny people. So the creative possibilities are really interesting. The quality of images, because of the different way they focus onto the sensor, that looks very different as well. It's more like film. Now, there are drawbacks. People who've reviewed them say they're hard to handle, hard to keep them steady. You need tripods. You have to know what you're doing. But I think the creative possibilities are really interesting. I think we're going to see some high-definition films produced on these things start to emerge on the web. And I'm just really interested. I want to see what people make with this stuff. I think it's quite exciting from a visual point of view.
So 3D televisions and miniature laptops, all very futuristic indeed. That was Naked Scientist Mira Senthilingam talking to our resident tech expert Chris Vallance and the BBT's technology correspondent Mark Ward about the technology that we should be looking out for because it's coming our way. Greg's on the phone. He's in Essex. Hi, Greg.
Hiya. Well, they say they've just put 20,000 tonnes of salt down on the roads, most of which are going into ditches, which go down to the water table. I'm just wondering, how long is it going to be before, in a drought, we're not going to be able to drink water from in the ground because it's all going to be brackish?
That's a very good question, Craig. Yes, all the salt is going to go down into the water table eventually. It's dissolved in water. It's going to run down where water is. It's either going to run down the streams and down into rivers, but out into the ocean when it's not going to make much difference. But the stuff which goes into the water table will make some difference. Locally, it could be an issue. I expect when you've been putting a lot of salt down, that it's probably going to have a significant effect on the degree of saltiness in the ditches down the side of the road, but overall it's probably not going to be very big of an effect just because how big the UK is. 1 millimetre of rain over a square kilometre is equivalent of 1,000 tonnes of water falling on it. The UK is 240,000 square kilometres, so just 1 millimetre of rain, less than a 20th of an inch, is going to be equivalent of 240 million tonnes of water.
Although, to be honest, that's not all falling evenly and uniformly like that, so there could be some areas that could end up with local salt build-up, but it's trivial really in the grand scheme of things.
But I think over any significant area there's going to be enough rain that's going to dilute it down to a point where it's not going to be a problem to drink.
Thank you, Dave. That's reassuring, isn't it?
I've got another salty question here as well. We've actually had a couple of listeners who want to know why the sea is salty.
This is actually quite simple, and it comes down to the fact that we have a hydrological cycle, so the sun puts energy into the Earth. Each square metre of the Earth's surface, on average, gets energy at the rate of about 1 kilowatt from the sun. This energy goes into the seawater, and the water molecules gain enough energy sometimes to evaporate, so you have water vapour which leaves the sea and goes up to form clouds. Those clouds then travel over to land. When they're forced to rise over things like high mountains, then in order to rise, they have to rain. They lose some mass in the form of water precipitation. That fresh water comes down out of the clouds and lands on the ground. It goes into rivers and streams, and it picks up tiny amounts of minerals and salts, which it dissolves on its way percolating through the ground and then in the rivers. There's not that much there, so the water tastes fresh. You can just detect trace amounts of these chemicals in the river water and in pond water. But as it works its way down to the sea, of course, it then takes with it those salts, and when the water then re-evaporates from the ocean, that's just fresh water evaporating, the salts get left behind. So over millions of years, you slowly accumulate salts in the sea to the level of salinity that we see today. And the sea isn't actually going to get much saltier, because once you get to a certain threshold concentration, you start to get other chemical reactions kicking in which limit the accumulation any further of any more dissolved ions and salts. So as a result, it just contains at the level that it's at. Dave?
Because actually the way we get most of our salt from is edges of the sea, very shallow, ancient shallow seas, where there's lots of evaporation, like the edge of a desert. So the sea keeps flowing in, lots of water evaporates, and the salt crystallises out. And that often gets buried. There's huge amounts of it under the North Sea. There's quite a lot in Cheshire. So they're just going in and mining it out and digging it out.
And you can go to Poland and go to some very famous salt mines, which were these salt pans, weren't they?
Yep.
Absolutely amazing. If you have a question for The Naked Scientist, the email address, chris@thenakedscientist.com.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
It is The Naked Scientists with Chris, Dave and Helen. Dave has just vacated to go to the kitchen for his kitchen science experiment. We'll be hearing from him and his microwave very, very shortly. But first, it's time to answer a very important question. Helen.
It's Question of the Week. It's time to invite Diana O'Carroll back into the studio. Hello, Diana.
Hello. We're all a bit 80s this week, so I thought we'd do a robot dance.
Hello, this is Paul from New Zealand. My question is, a year or two ago I was daydreaming of a light suit of armour which folk could put on, and it would help uncoordinated fools such as myself to do Tai Chi or ballroom dancing, either by giving me an electrical prod in the left leg or the right leg or left arm or right arm or whatever. Any comments?
So, could we see breakdancing across all the generations?
My name's Noel Sharkey, and I'm a Professor of Robotics and Artificial Intelligence at the University of Sheffield. I don't think anybody has a plan to make a suit like that, but I think now that your listener has said it, someone might do it. I mean, my immediate thoughts are the exoskeleton suits that have been developed by the American military and also by a Japanese company called Cyberdyne, and they're leasing these exoskeleton suits to elderly people at the moment. And what it is you put the suit onto your body, and it's very, very thin, lightweight metal, and it goes up your body, so it will detect how your muscles are moving, and then it will move as you want. So it will lift you out of your chair, you can run upstairs, and you can lift heavy weights. I know they can be remote controlled, so you could have somebody remote controlling it and getting you to do the right dance steps, or you could program it to do the dance steps. But another point I thought was that maybe you could use one of those sensitive dance floors. An ex-student of mine has developed one in Limerick, the University of Limerick, Neil Griffith. And what it is, it's a floor covered with pressure sensors. And Irish dancers can use this floor, and what happens is it's made up of squares, and the squares will light up to let the dancer know where to go. And if they put their foot on it, there's a pressure sensor that detects where they've gone. And what could happen in combining the suit and the sensor floor is that the floor could light up and let the person know where to go. And if they didn't go there immediately, the suit could go there for them, thus giving them feedback. So that would be my solution to it, but very, very expensive at the moment.
So if only you could have one of those to fight off an alien. But perhaps a dance-regulating exoskeleton isn't quite so far off, and you might need a good set of batteries for a dance-off competition. But on our forum, JNA said that even if they could weave the electronic nerves of an exoskeleton into your brain, you'd still need to take tango lessons. Well, from dance music now to the sweet tune of the milk steamer.
Hello, my name is Mouse. I work as a barista, and so I steam a lot of milk. When the milk gets to 140 degrees Fahrenheit, the sound that it makes abruptly drops pitch significantly. So I'm wondering why this happens.
So, why does milk change its tune when it reaches a certain temperature? Let us know what you think via email, and that's chris@thenakedscientist.com, or on the web, and that's thenakedscientist.com/forum, where you can read what other people thought, as well as putting down your own answer.
Thank you, Diana. You'll be off to the coffee shop to answer that one next week, presumably.
I certainly will, yes.
OK, and if you want to catch up with any previous questions of the week, Diana O'Carroll has got a Question of the Week podcast, and you can download about 100 of them or so. They're all on iTunes. This is The Naked Scientists with Chris, Dave and Helen, and in a second we'll be finding out what happens when you microwave an ice cube.
Bringing the facts to bear. The Naked Scientists.
And this is The Naked Scientists with Chris Smith, Helen Scales and Dave Ansell. This week we're answering all of your science questions, including a really quite important question that Helen's going to talk to us about now. Helen.
Yes, earlier on we asked Dave to get a couple of microwavable cups, place some ice cubes in one, a similar amount of water in another, and then put them both in the microwave together, switch them on and see what happens. Well, instead of trying to get the microwave down here into the studio, we've sent Dave upstairs to the kitchen. We've put him where he belongs, and he's about to test out the experiment with some help of Ben. So, guys, have you finished the washing up?
I'm just nearly finished now, actually. Hold on, just give me a second. There is a dishwasher here, so I probably
Mine's
should
2
have just
sugars,
used that.
thanks.
Right, yeah, well, Dave has come up to join me in the kitchen. So, Dave, we're microwaving water and ice, is that right?
Yep, that's the plan. So I've got some nice ice cubes here. We want to try and make this test as fair as possible, so we want to use exactly the same amount of ice as water.
And to do that, we're going to weigh the ice that we're using, yeah?
That's right, so I'm going to get maybe 3 ice cubes.
OK, nice cold ice cubes. Now, obviously, these have come from our freezer here, so they're very, very cold. They're actually quite dry to the touch. Is that important?
That will certainly help, as become clear later. So we've got about 36 grams of ice cubes.
Okay, so we've put those in a microwavable cup, so we know that that will be safe, because obviously we don't want to put anything in the microwave that won't react well to the microwave. And so now we need another 36 grams of water.
That's the plan, so I'll pour that in here.
Okay, 822, nearly there. And 30, come on Dave, a little bit more. And that's near enough. Okay, so we're making sure this is definitely a fair test by having the same amount of water and ice. And they're both in microwave-safe cups. And we're going to put them both in the microwave.
Yeah, that's the plan. So I'll put these in. Put them in symmetrically about the centre, so they both go through the same number of hotspots.
So this means that they are both the same distance from the centre of the turntable, and that means that they'll go through all of the same hotspots. They'll both get exactly the same heating, again, just to make sure this is fair.
That's right. So we'll put that on, and we'll turn it on, and we'll see if we can see whether the water boils or the ice melts first.
OK, so let's just shut the door and get this switched on. How long do you expect this will last, Dave?
In the past, maybe 20 or 30 seconds, so we'll have to fill until then, Ben.
So it's not quite like defrosting a microwave meal where you really need to put it on low heat for quite a long time.
Well, yeah, it's much, much smaller than microwave meals, so you'd expect everything to happen a lot quicker.
So we're just watching these 2 cups of water, and at the moment, really, nothing's happening, Dave.
Not the most exciting of races yet, but we'll give it some time. We'll see what happens.
Ben, can you do my curry? It's in the freezer. When you finish, can you just pop that in, because it'll be ready for after the show then?
I will, but Dave has just opened the microwave because the water has started boiling. So, but the ice is actually still totally solid. I mean, listen to this. I hope you can hear that. That's the sound of solid ice cubes in a glass. But the other cup, was boiling away, was bubbling away madly. Dave, I really would have expected that the ice would have melted first. Surely it doesn't make sense that you can raise the water so high that it boils, gets to boiling temperature, and the ice is still solid.
Well, there's 2 effects. One of them is that to melt ice takes an awful lot of energy, about 27 kilojoules per milliliter, whereas heating of water takes about 4 kilojoules for every degree centigrade. So you still need a lot more energy to boil water than it should take to melt the ice.
So it's the phase change that takes up all the energy. You're not just raising the temperature, you're actually changing the phase of the material.
Yeah, that's right. But you can see this ice hasn't melted, so we haven't even started putting that energy in. So there's something else going on. The other thing that's going on is to do with how a microwave works. The way a microwave oven heats something is by giving out a kind of light, a kind of electromagnetic radiation called microwaves, surprisingly. These come out of the little panel at the side of the microwave. And these electromagnetic waves, and they make the electric field point one way, then the other way, then one way, then the other way.
So basically you're just moving the electric field inside this microwave oven up and down really very quickly.
Yeah, that's right, about 2.5 billion times every second.
Wow, so really very quickly. So how does that interact with the water?
Well, water molecules have got a positive end at one end, positive hydrogen atoms, and a negative oxygen atom in the middle.
Okay, and don't we call this a dipole when you have these 2 different ends on the same molecule?
That's right, 2 poles, and therefore if the electric field points upwards, then the negative oxygen atom is going to rotate to point along the field, and if it points downwards, it's going to try and rotate back again. And this rotating, it absorbs energy, and that's what's heating it up.
So the microwave radiation makes the water molecules move up and down millions of times, and that gives it extra energy, it heats it up.
Yeah.
So why hasn't this happened to the ice?
Well, in ice, all the water molecules are locked together in a big crystal structure, which means they can't rotate. They're locked much too tightly to rotate. So because they can't rotate quick enough for the to absorb the microwaves, they can't absorb very much energy. So they don't heat up very quickly.
So it's not just that it takes much more energy to defrost, as it were, the ice. It's actually not absorbing the energy in the first place.
Yeah, it would probably take less energy to defrost the ice than it would to boil the water, but it's just not absorbing it.
So is this why we have to be very careful when we defrost something in the microwave? Because otherwise we get patches that are burning hot and other patches that are still frozen.
That's right. If you defrosted something on full power in the microwave, you'd find that some patches maybe might just start melting first. And as soon as it melts, it suddenly absorbs microwaves maybe 100 times better than the ice around it. So the patches which are already melted are going to get very hot, overcook, and meet very, very quickly, whereas all the ice is going to still be solid. Which is the reason why defrost settings on the microwave are very, very slow. In fact, they only turn the microwave on maybe for a few seconds, and they turn it off for 20 or 30, then on for a few seconds. So the heat from the hot areas has got time to spread out and melt more of the frozen chicken or whatever without cooking it. And so very gently you can heat it up and melt it.
Well, that's fantastic. And I know that you are very fond of doing experiments with microwaves, and we've got quite a few on the website at thenakedscientists.com/kitchen science, including measuring the speed of light with a microwave. So are you going to put a full explanation of this so that people can read it online?
Yes, in a couple of days' time that'll be up.
Fantastic. So go online, have a look. There's a few other experiments you can do. And Chris, I will get your curry out of the freezer and get it in. It should be nice and toasty, ready for the end of the show.
Excellent. That's all. We're always a bit hungry by the end of the show. Thanks, guys. That was a brilliant kitchen science. So make sure you check out the website, thenakedscientist.com/kitchen science, to have a look at what we were up to. Now, I've got a question here, which is, why does foil touching a tooth filling taste strange? What do you reckon, Chris?
Did you ever do the thing, Helen, when you were at school where you put your metal pencil sharpener in your mouth? I know you shouldn't because the blades are sharp.
Of course I didn't.
Did you notice you got that funny tingly sensation on your tongue? Have you never noticed that?
I've never tried. Now I want to try.
Certain pens that have a sort of the clip that you put over your pocket that's metal, and it's made of a different metal to the pen, and you suck those and occasionally notice a tingly sensation in your mouth. Have you ever noticed this?
I haven't, but I'm going to try now. But my pen's plastic, so that
won't work. But
not going to work.
The point is that when you mix two different metals together and you have an electrical conductor between them, an electrolyte, and saliva has got lots of salts in it, so it's an excellent conductor, you can get a chemical reaction happening between the two metals, and one metal, the more reactive one, will form ions, and it will give up electrons, which will flow through the electrolyte to the less reactive metal, and that's how the reaction occurs. And so as a result, if you touch two different metals, in this case they're touching metal foil with a filling, that's mercury silver amalgam, then the aluminium will dissolve to make some aluminium ions. You'll make some electrical current, which you experience in your mouth as this tingling sensation, and it will also react with the saliva to produce some hydrogen and some oxygen gas, perhaps, on the two different surfaces. And you will also then deposit some material on your filling. So you are basically turning your mouth into a battery, and that's why it happens.
Oh dear, that sounds terrible. Is that? It sounds pretty bad to me.
Well, I mean, I'm sure it's absolutely fine in small doses, and pencil sharpeners work because they're made of magnesium, which is why they're so light, and the blade is steel.
There you go. Hope that answers your question.
It certainly does. Thank you very much, Helen. And thank you also to Dave and to Ben and to the rest of our production team, Mira Senthillingham, Diana O'Carroll and Tom Simpkins. We have, unfortunately, run out of time. Now, next week, we're going to be looking at the science of love and sexual attraction. Why do we fall in love with people? Why do we want to spend the rest of our lives with certain people? Well, it turns out that it's all down to chemicals in the brain, and now scientists know pretty much what they are, and there may even be a nose spray that can make you fall in love. We'll find out about it next week.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientist.com.